Welcome to the content material for Class 3 of Engineering Statics. You should be watching this video before your third class. Today, we will be covering several important ideas that will provide a foundation for this course. In this lesson, we will cover the following topics. We'll talk about scalars and vectors, the rules for adding and subtracting vectors, and we'll talk about and describe the Parallelogram Law. All physical quantities in engineering mechanics are measured using either scalars or vectors. A scalar is described completely by its magnitude. These would be values that we're typically familiar with, such as length, mass, and time, and they can be positive or negative. A vector, however, requires both a magnitude and a direction to completely describe it. An example of a vector that we will see in this course would be force, or position, or moment. To show a vector graphically, we draw an arrow. The length of the arrow shows its magnitude, so a longer arrow means, if we're talking about a force, a stronger force with a larger magnitude. And the arrow also indicates the direction that it goes. So for example, this arrow is pointing 20 degrees away from the x-axis. When we write a vector, we might refer to it as the vector f. And when we write that in our text, we'll say that the f would write an f with an arrow above it. That's usually how I'll write it. And that's how you should write it on your exams and on your homework. However, in the textbook, you will see a bolded f. Both of these refer to a vector as opposed to a scalar. If we talk about the magnitude of f, just in terms of the magnitude of it only, so it's really just the magnitude of that vector f, we don't use the arrow overhead. It's important that we differentiate between scalars and vectors. So if we're talking about a scalar such as the magnitude, we need to write it this way, but if we're talking about a vector, it's very important that we include that arrow over top to indicate that we're talking about a vector. We can multiply vectors and scalars together. So for example, if we have this vector a, and we want to multiply it by 2, and 2 being a scalar, just the magnitude of 2, well, we see that it doesn't change the direction, but it does double the length. We can also multiply it by negative. It means that the vector now points in the opposite direction. And we can multiply it by numbers less than 1, which is the same as division. Because a vector has both magnitude and direction, we always need more than one piece of information to describe it. In 2 dimensions, we need at least 2 pieces of information about the vector. That could be magnitude of that vector in the x and y axes directions, or it could be the magnitude and the angle, so we could say u and theta. On the other hand, if we're talking about a vector that's in 3 dimensions, then we need at least 3 pieces of information about that vector. So that could be its magnitudes in the x, y, and z directions, or it could be the magnitude and 2 angles, which we can call theta and phi. If we don't have enough information, we can't fully describe that vector. Now, if we want to add 2 vectors together, we can do that. This is the idea of finding the total force of 2 different forces combined. So for example, if this hook here has these 2 chains attached to it, there might be a force in F1 and a force in F2, and the total force of them combined we can call Fr, or the resultant force, or the resultant vector. And so we see that that resultant vector, Fr, is equal to the sum of these 2 vectors, F1 and F2. Now we can imagine, as it's drawn here, the addition of these two vectors as a parallelogram. So we can move F2 over here and F1 over here, and we see that the shape is a parallelogram. And so we see that F1 plus F2 is just the same as F2 plus F1. So it doesn't matter the order that we add them. It adds up to the same resultant vector. And we can use this information to solve problems, and I'll show you how to do that. So remember first that in a parallelogram, these two angles opposite each other will be the same angle, and these two angles opposite each other will also be equal to each other. And that all of them added together are equal to 360 degrees. In the same way, because we already saw that F1 and F2, the sum of those is the same, regardless of the order, we only need to do it once. And in this case, we see that we have a triangle. And we can use the properties of a triangle to solve many things. So remember that the sum of the angles inside the triangle always add up to 180 degrees. We can use some other ideas from trigonometry to help us in adding forces together as well. The first one is the law of sines. So in this triangle, we see that there are three sides to it, A, B, and C, and we want to draw the angle, we want to label the angle that's opposite A, we can call that one little a, and the one opposite B is B, and the one opposite C is C. And the law of sines tells us that the ratio of A over the sine of the angle opposite of it is equal to the same ratio. So B over sine B and C over sine B. This will be very useful for us. And we can also use the law of cosines to figure out the magnitude of this. So the length of this side of the triangle C is equal to this value. So the length of A squared plus B squared minus 2 times AB times the cosine of this angle that's opposite of it. And so we use both of these properties of triangles to solve for adding two vectors together. And I'll show you 3 examples of that now.
Okay, so in this example we see that there is a screw eye or a hook here with 2 ropes attached to the hook. And there's a force pulling on each of those 2 ropes, and we'll call that F1 and F2. And what we're trying to figure out is the resultant force. So we're going to call that FR. We're going to call that the resultant force, FR. And we want to know what that is. And we also want to know the direction of that force, and we'll call that angle of the force, we'll call that phi. And so we're trying to figure out those 2 things. So the first thing we need to do is we need to draw a diagram for this. So we're going to draw force 2 and force 1. If we do it, there's some resultant force, FR. And so we can use the parallelogram rule to say that this is F2 and this is F1. And so we have now the shape of a parallelogram. And we need to start to figure out the angles within that parallelogram. Well, we know already that this is a 90-degree angle, and we know that this is 15 degrees, and we know that this is 10 degrees from what's shown in the picture. So we know in between is 90 minus 10 minus 15, so that's 65 degrees. So inside here is 65 degrees, and we know as a parallelogram it's the same on the other side. And we also know that a parallelogram has 360 degrees inside. So this angle over here, which I'm going to call C, is going to be equal to 360 degrees, which is the total amount of angle, degrees within inside the parallelogram, minus what we have already, minus 2 times 65 degrees, and divide by 2, because this will be the same angle over here on the other side. And we see that when we do that, that angle is 115 degrees. So we know that angle there, C, is 115 degrees. At this point, we can draw a triangle here. We have FR, F1, and F2. And so we have a triangle here. And this is going to be some angle which we'll call theta, and we know that this is C, or 115 degrees. And now we can use the law of cosines, right? So the law of cosines says that in a triangle, we have C, B, B, A. We know that the length of C is equal to the square root of A squared plus B squared plus AB cosine of C. And if we look at our diagram here, we see that the force of the resultant, Fr, is equal to F1 squared plus F2 squared plus F1, F2 cosine of C. So when we put our numbers in here, we already know, we're told in the problem, that F1 is 100 newtons, F2 is 150 newtons. So we'll start putting those numbers in there. Okay, so we see that 100 newtons squared, 150 newtons squared, plus the times the cosine of 115 degrees. When we put that in there, we find that the magnitude of the resultant force is 212.6 newtons. And we can write it this way using 4 significant digits. If we wanted to do 3 significant digits, we could say 213 newtons. Either one of those answers would be acceptable. Now, so we've done this part. We've determined what the resultant force is. Now we need to figure out what that angle, what the direction of it is. And what we're defining here is that the force of the resultant is some angle phi. We know that force 1 is 15 degrees. Sorry, not 10 degrees, 15 degrees. So if I call this inside angle theta here, between F1 and F2, this is theta. Sorry, not F1, not F2, but Fr. And this one is phi. We know that phi then is equal to theta plus 15 degrees. So the question is, what is theta? Well, we can draw a triangle. Again, come back. I'm just going to draw a general triangle, right? B, A, C. We call this angle B, this angle C, angle A. So A is opposite to A, C opposite to C, B opposite to B. And we use now the law of sines. Okay, the law of sines. Law of sines says that B over sine of B is equal to C over sine of C. And we see then that B here would be F2, right? F2, F1, and Fr. Okay. This is theta, and this is C. Okay, so F2 over the sine of theta is equal to Fr over sine of C. So we see that sine theta, we solve for sine theta, that's what we're trying to figure out, is equal to sine C times F2 over Fr. We start putting our answers in, our values in here. And we see here the answer. To solve for that, we find we have to take the inverse of theta, right? So theta is going to be equal to the sine inverse of that number. And we find out that theta is equal to 39.8 degrees. And so the angle that we were looking for is theta plus 15. So we find out the direction of that force is 54.8 degrees. Okay, so here's our answer. Fr is equal to 212.6 newtons, right? Okay, so that'll be the first example that we look at. Okay, in the second example here, we have a single force pulling on these two hinges here, these two rods, and that force is, I'll call F. F is equal to 600 pounds. Okay, so I'm calling that force F, 600 pounds. And we want to break that force F into two components that are along the U axis and the V axis that are drawn there. So the first thing we want to do is we want to start by drawing a diagram. So we have our force F, and we're going to have some force, we'll call it FV and FU, along these two axes. And we're going to set up a parallelogram. Okay. So we know that FU is along this axis, and this is 30 degrees here. And we're told that this over here is 30 degrees as well. So what we want to do is we want to move FV to be down here. So we want to move FV over here because we know that F is equal to FU plus FV. That's what we're saying. FU and FV. We're breaking up F into two forces, FU and FV. So we know that F has to be equal to FU plus FV. So we just need to know these angles. Well, we have a triangle here. We know that this is 30 degrees. And we know that over here is 30 degrees. This is 30 degrees. And so we know that this angle there is 30 degrees. That comes from this information here. Okay? So we know that there's 180 degrees in a triangle. So if we already have 30 at this angle and 30 at this angle, we know that the angle in here is then going to be that 180 minus 30 minus 30, that equals 120, because we want to have all the angles add up to 180 degrees inside the triangle. So now that we have this information, we can draw, again, I'll draw a generic triangle, ABC, right? Opposite angles. And we're going to use the law of sines. Okay, the law of sines. And so what we're trying to figure out is FU is equal to what and FV is equal to what. That's what we're solving for. So we see in our triangle that this is F, this is FU, and this is FV. And we know these angles. This is 30, 120, and 30. Okay. So we want to solve for FU. Well, we'll put A over sine A is equal to C over sine C. And so that is going to be A is F, right? C is FU. Okay, so we see that F over sine of 30 is equal to FU over sine of 120 degrees. We solve for FU. We see that FU is equal to F times the sine of 120 degrees over the sine of 30 degrees. And when we solve for that, we find that FU is equal to 1,039 pounds. Again, so here's 4 significant digits. We don't need any decimals because there's already 4 significant digits. And the next thing we want to do is solve for FV. Again, we come back up here. We see that B over sine B is equal to C over sine C in our generic triangle here. And we replace our values in there. We see that FV over sine of 30 is equal to F over sine 30. So we see that F is equal to FV. So that's equal to 600 pounds. Okay, so now we have our answers that FU is equal to 1,039 pounds, FV is equal to 600 pounds, and here's our answer. Okay, in the last example that we're going to look at in the class, we see that there's a ring with 2 forces pulling down on it, F1 and F2. And we know these angles here. We know the angles between these 2 forces. And we know that the total force pulling down, I'm going to call that FR, which is equal to F1 plus F2. So the total force of F1 and F2 combined is equal to, we're told, 1,000 newtons, or 1 kilonewton, it says. And we know the angle then. And so the question is, what is F1 and what is F2? What is the magnitude of those 2 forces so that the total force is not only 1,000 newtons, but also that it's pointing straight down. It says directed vertically downward. So the resultant force is vertical downward and has a magnitude of 1 kilonewton. Okay, so what we're going to do is, again, always start by drawing the diagram. So we know that there's some resultant force which is equal to F1 plus F2. So we're going to make our parallelogram, right? FR, we have F1, and then we're going to put F2 at the end of F1. And we need to know the angles. Well, we know that this angle here is 20 degrees. We're told that. And we also know that over here, this angle, says theta, is equal to 30 degrees. We're given that information. So that means that this down here is 30 degrees. And so we know that inside the triangle is 180 degrees. So minus the 20, minus the 30, that gives us this angle over here, which I'm going to call C. So we know that C is equal to 130 degrees. Okay. So we're going to again use the law of sines. So law of sines tells us, okay, if we draw B, A, C, okay, call this little c, little a, and little b. Well, law of sines tells us that b over sine of b is equal to c over the sine of c. And we know that this is fr, this is f1, and this is f2. And this is 130 degrees, this is 20 degrees, and this is 30 degrees. So we just start putting the information in. So B is F1, so F1 over the sine of 30 is equal to FR over the sine of 130. And we solve for F1. F1 we can solve. We know that we know the value of FR is 1,000 newtons, and when we put that in, we find that F1 is equal to 653 newtons. Okay, Next we would have solved for F2. Well, again, come back to our information. A over sine A is equal to C over sine C. In other words, F2 over sine of 20 is equal to FR over sine of 130. Solve for F2, and then FR we find that F2 is equal to 446 newtons. So, our answer, we want to know what F1 and F2 were. F1 is equal to 653 newtons, while F2 is equal to 446 newtons. But again, we should always check that our answers make sense. It makes sense that the values of F1 and F2 should be less than the resultant force, right? If Fr is equal to F1 plus F2, then we know that they should be less, that the magnitudes should generally be less than that, right? And I should go up here and should point out that what we're talking about is that the vectors add up. So the vector force of Fr is equal to F1 plus F2, not the magnitudes. So that's just a clarification about the difference between writing Fr is referring to the vector, and Fr is equal to the magnitude, right? When we don't have the little hat on top. Okay, so that's it for the third example. Hopefully at this point you've seen a couple of examples. In class, we'll start off with a quiz that will be similar to this, and we'll review that in class. So I'll see you there on class 3.